Okay. Hello, students. Today we will learn about the object detection pipeline again. So in lecture 4, we learned about the fast RCNN algorithm and fast RCNN algorithm and also the RCNN algorithm. These algorithms are two-stage algorithms, okay? But and also we learned about the DTR algorithm, okay? So which is based on the transformer architecture, okay? So previously, transformer was derived from the natural language processing domain, but nowadays it is replacing the CNN algorithms, which was the state of the art, but now they are replaced with transformer architectures, okay? And today we will add some more explanation on these DTR algorithms, okay? So we will, this object detection pipeline, the second materials are dealing with the DTR algorithms. Actually, these DTR algorithms were published in 2020. Okay, so like 3 years ago, this DTR was proposed, and after that, there are a couple of algorithms which is proposed to improve the conventional DTR algorithms. Okay, so today we will learn about that. Okay, there are some limitations in DTR algorithms, so we will learn about it during this class. Okay, and before that, I will briefly review the DTR algorithm. If you are not familiar with this, then please review lecture 4. Okay. So in DTR, we are still using some CNN features. These image features are some features extracted from ResNet, which is pre-trained with the ImageNet. Okay. So we are still using CNN in transformer. Some portions of the transformer architecture, we are still using CNN. Okay. And this image feature, it becomes the query key values in the encoder. And actually there are decoder after encoder, right? Image feature vector, it becomes query key value, and we apply the self-attention mechanism, okay? The query key are first dot producted, and afterwards it is multiplied with the value, okay? And after doing this operation, we obtain the improved image feature, okay? So anyway, we obtained the vector, which is same dimension as the input vector. And this is kind of improved version of the input. Okay, so because our input is image feature, we can call this output as the improved image feature. Okay. And in the decoder, we input the object queries. In DTR, there is no explicit meaning, okay, for these object queries. So people are sometimes confused about the actual meaning of these object queries, okay. In NLP, this was some, when the transformer is applied to the translation task, these object queries are some other language sequence, right? And the encoder, it is also the image feature, this is some other language, and we input the start token and also the rank, the output, first output of the transformer, again as the input to queries of the decoder, right? We sequentially input the output of the decoder, right, to estimate the next output, okay? You can review lecture 4 for this, right? But in the image domain, there is no sequential meaning. So we don't have to do that in sequential manner, like in the NLP domain. But we can anyways input like 300 to 500 queries simultaneously to the decoder, okay? And we first apply the self-attention mechanism inside the decoder, okay? And this output of the self-attended output are input to the cross-attention module of the decoder, okay? And here, it is added with the original object query, right? So actually here, we are visualizing it like this. So this is the cross-attention module, right? And firstly, their self-attention module was here, but we skip it when drawing this figure. And we denote decoder embeddings as the output of the self-attention module of the decoder. Okay, so this is called as decoder embeddings. And the object queries are sometimes called as learnable queries. And they are added to these embeddings to be the query for the cross-attention module. Okay. And there are 300 to 500 object queries inside the decoder, and this is actually used to reveal the ground truth. So let's say there are 5 ground truth objects inside an image, okay? Then among these 300 to 500 object queries, their output needs to estimate this ground truth object, and rest of them, maybe this number of queries are mapped to background. Okay. So among these, most of them are mapped to the background, while some of them are mapped to the object inside an image. Okay. So this is happening in the DTR algorithm. Okay. And also, you may also remember that the reason why this is called as the cross-attention module is the queries are from the decoder embeddings, but the value and keys are from the image features, improved image features outputted from the encoder, right? And actually that is also visualized here. So image feature, this is actually the improved image feature, and they are inputted here. And for the key, the positional encoding is added to the key, and they are becoming the value key query for the cross-attention module. And this is further used in later operation, and eventually they predict the bounding box and class, okay? So this is the DTR algorithm. And also, these object queries are fixed floating values during the testing time. And they are actually learned during the training time, okay? We can flow the gradients until here, and these values are updated to maximize the accuracy for training data. Okay, and they are fixed, and they are that fixed values are used for the testing time. Okay, and no explicit meaning. They don't have any explicit meaning, but they are just trained values. Okay, right? So in image domain, they don't have explicit meaning. Okay, and this causes some weakness in DTR. So maybe afterwards you can realize that how to improve these object queries. Okay. Actually, there are some limitations in DTR. Even though it surpasses the accuracy of the fast RCNN, it still has some limitation. Okay. Firstly, we can say that DTR is takes a lot of time to converge it, to make it converge. Okay. It takes 10 to 20 times slow for training compared to the fast RCNN algorithm. Okay. And also it exhibits the scale problem. Uh, it is not effectively detect the small object. Okay. And to tackle the challenge, to tackle the scale of the object, to capture diverse scales, diverse object in diverse scales, we have to have the encoders which have the multiple scales, okay? But DTR is already complex, right? So we are involving the multi-scale encoder in the DTR, inside the DTR is not that trivial, okay? And also the attention mechanism, it requires the quadratic computation with respect to the pixel numbers, okay? So this is the limitation of DTR, okay? It takes heavy complexity and slow convergence, okay? So the deformable DTR is proposed. It uses the deformable attention mechanism, okay? So it is published in ICLI 21, okay? So we can draw the figure for the deformable DTR like this, okay? In deformable DTR, basically the attention mechanism, mechanism is simplified. Sorry. Okay. Uh, my connection was not good. Anyway. Hmm. Okay, now it works. Sorry about that. So in deformable DTR, the attention mechanism is further optimized by reducing number of keys. Okay. And also it removes the actually there are dot product between keys and queries, but we will actually remove this. Okay. Okay. Number of values we remove. Okay. So this is the contribution or actual contribution of the deformable DTR. So from the query features, this XQ is denoting from the feature map, input feature map, we can select one pixels in the feature map, and that would be some vector, right? And the reference point, this is denoting the position, 2D coordinate of this point, okay? And what they do is they choose the value by sampling some offsets, okay? For this query, they select some values, okay? So previously, the attention mechanism densely applied to all the pixels inside the input, okay? For all input, for individual input, all of the other inputs are dot producted with that input. That was the attention mechanism. But here, they select only sparse neighbors. They only select the sparse neighbors, and they are the sampling offsets. They are actually estimated from the query feature. Okay. And again, the attention weight previously this was dot producted between the keys and queries, right? But this will make the this will make the situation complex, right? So because there are if there are n keys and n queries, then their complexity becomes n squared, right? Because of this attention weight calculation, the attention mechanism, it is becoming complex, okay? So instead of doing this dot product between n multiplied by n vectors, they directly estimate this attention weight from the queries using the linear operation. So in deformable DTR, there is no pairwise dot product anymore, okay? So values are obtained by sampling some offsets, okay? And also the attention weights are obtained by the linear layer, okay? And they are produced, and they are for multi-heads, they are applied with the linear layer again, and they are mapped to the final output, okay? So this is the deformable attention mechanism happened in the deformable DTR, okay? So, and also this is the deformable attention for encoders, okay? So these reference points are the coordinate for query pixels. This is the query pixel feature, right? From the entire feature map, for specific 2D coordinate, we get some query feature, pixel-wise feature, right? And that coordinate values are becoming the reference point, okay? But in the decoder, when choosing the queries, we don't have any feature map, okay? So here, for encoder, we have the image feature, right? And we have the XY coordinate for this image feature, but object queries, when doing this, there's no spatial meaning for object queries, right? So for the decoder, for each individual query, we infer positional, we infer reference point using some linear layer again, okay? And do the same for self-attentions, okay? And do the similar thing for cross-attention mechanism. When finding reference point, we need to infer some reference point from the query, low query values via the linear layer, okay? And we predict the offsets, sampling offsets, and also the attention weight instead of by doing the dot product between query and key to find this attention, we directly estimate it from the query itself. And also we find the values, their offsets from the queries again, okay? So the attention is obtained for offset points of the reference point. So I will show you in detail this formula again in the later slide, okay? And we then predict the bounding boxes relative to the reference point, okay? In here, we output the bounding box coordinate, and that's actually the relative positions to the by regarding the reference point as the center point, okay? Actually, we estimate the residual values for the bounding boxes, okay? That's here. So you may remember the attention mechanism was like this, right? Query key are dot producted and they are applied with softmax and then multiplied with the values, right? And if we have multi-head attention, the head attentions are concatenated and applied with some linear layer, right? This was the multi-head attention. And we can reformulate it like this. Okay, so we can say this as the dot product between QK, okay? And M is denoting multi-head index, okay? For all key, but here, I think the notations are not clear enough. This is actually the value, I think. If you think this as value, the things are becoming more clear. So this is the query. And they are multiplied with the weight. And actually, this is meaning some value, I think. And if it is multiplied with the attention, and if we add it for multiple head and apply some linear weight, then it's the multi-head attention. We can actually rewrite it like this. Rewrite this like this, okay? So in deformable DTR, they are saying that the original multi-head attention, they could be rewritten as follows, okay? And what they do in deformable attention is can be rewritten like this, okay? So this is I said this was the value, right? This is the attention weight by the query, but originally it have to be dot producted between query and keys, right? By dot producting these two values, we find the attention, and afterwards we apply softmax, and we normalize it and apply softmax and multiply with the value. Okay, this is the attention mechanism. But here in deformable attention, we find value by finding the offsets. Okay, by estimating the offsets via the linear layer, and also this is also estimated via the linear layer, right? But except for these two facts, the attention is inferred from the query itself, and also the values are obtained by this manner. The other mechanisms are same as before, okay? The number of values are a lot reduced, okay? So, and also here the computation is a lot reduced. So that is the reason why this deformable attention is faster than the conventional attention, okay? And another thing we have to also see is here the X, which is the feature vector, feature map actually, is having multiple layers, okay? Previously, I said to capture a small object where also the big object, object in diverse scales where we have to encode the feature in multiple scales, okay? So now we are encoding the features in multiple scales, okay? And we have another loop for this L here, right? So this is called as multi-scale deformable attention mechanism, okay? Actually, in deformable DTR, it reduces the attention complexity of the attention mechanism, but instead, it increase the scales for the encoder, right? So yeah, but still it's faster than the conventional DTR. Okay, so it reduces the complexity of the DTR. At the same time, it can accelerate the training, okay, by doing this. And it has two more modules to improve the performance, okay. The first thing is iterative bounding box refinement. Actually, there are multiple layers in the decoder, right? So here we can say this is having multiple layers. So we have multiple cross attention or attention mechanisms in the decoder, right? So at each decoder, we predict the bounding boxes, okay? But we can improve the previous bounding box by estimating their residuals, okay? So this is the next layer's prediction bounding box prediction, and this is the prediction from the I+1 layer, okay? And we detach, this is the detach of the gradient. To make the training simpler, unless we detach this node, we have to flow gradients for previous layers, right? So the training becomes a lot slower, right? So by detaching these layers, we do not have to flow the gradient to the first layer. Instead of that, we can flow gradient for these current layers, okay? So they are saying that this is helpful for simplifying the training, okay? Anyways, they iteratively refine the bounding box at each layer's output, okay? And another thing we have to remember is the deformable DTR, it is also concerning the object queries, okay? Here, it is the object queries. The decoder input is object queries, right? Here, the input is image feature, okay? They are saying that because these object queries are not related to spatial coordinate, the performance is not that good. So motivated by two-stage object detectors such as fast RCNN, the region proposals are generated, okay? Here, from the encoder output, this is the improved feature, right? They estimate object proposals here. And then they use this to improve the object queries to have some spatial meaning, okay? They actually add this information when constructing the queries to the decoder. This is similar to positional encoding, actually. And they are saying that by using this method, the deformable DTR, their performance is slightly improved, okay? So you can see here, so firstly, you can see this is the original deformable DTR. And if you use iterative bounding box refinement, the performance is slightly improved. And by additionally using the two-stage things, by obtaining some proposals and use it as the input to the decoder, the performance is also slightly improved, okay? And you have to see this. So this APS is the performance for small object, and this APM is the performance for middle scale object, and APL is the performance for large scale object, okay? Compared to fast RCNN, the DTR, their performance was less for small object, okay? This is comparable, middle scale is comparable, and for large scale object, DTR is far better. But for small scale object, the DTR was less than, their accuracy was less than that of fast RCNN, right? But the deformable DTR, it is better than fast RCNN for all scales, right? And it surpasses DTR as well, even though their training epochs are 10 times less than the DTR. it surpasses DTR performance. Okay. So by simplifying the attention mechanism, DTR is further optimized, okay, in deformable DTR, okay. So this is also the graph showing that, so original DTR, it usually takes 500 epochs to be fully trained, but the deformable DTR, it only takes around 50 epochs, okay, to be matured, okay. So this is the merit of deformable DTR. It takes less time than DTR during training, and actually it is faster than DTR at the inference time. Also, it performs better than DTR. Okay, that's the merit of deformable DTR. And the next thing I want to tell you is conditional DTR. So from now on, I pointed out that object queries in transformer was not having proper meaning. So previously in NLP, these queries are some inputs having some meaning, right? But in in image domain, it does not have any explicit meaning, right? But it is dot producted with the keys and values from image feature, right? Actually improved image feature, right? In cross attention module, it is cross attended to keys and values which are actually from the image feature. These image features are having some spatial meaning, but object queries are not having that kind of meaning, okay? And actually, they are cross-attended and to infer some bounding box information which have the spatial meaning again, okay? So people are becoming to thinking that because these object queries are not having any spatial information, the DTR training takes a lot of time, okay? If we give object queries some spatial meaning, this is assumption. They assume that the DTR training could be improved, okay? Okay. Object queries are not having any image-specific information, but we can still visualize it in this spatial domain, okay? So when we train DTR for 50 epochs, some of their output, this green is the ground truth, and the yellow are predicted attentions. They are not effectively learned yet, but we train DTR for 500 epochs, it eventually can find it, okay? So people think, becoming to thinking that the reason why this slow convergence is due to the fact that object queries is not having any spatial information, okay? So hard to map queries to those partial keys, it causes the slow convergence of the DTRs, okay? So in conditional DTR, the researchers are proposed to giving some spatial meaning to the object queries. Okay. And also, they divide spatial query and content query. So they actually divide queries, object queries into two, which is the spatial query and content query. Spatial query is having some coordinate information, and content query, it is having some, maybe you can think this as the decoder embeddings without any spatial meaning, okay? Usually, we think decoder embeddings obtained from the self-attention of previous object queries as the content query. And the learnable queries, this is as the spatial query. And also, we think the encoder output, the improved image feature as the content key, and positional encodings, we think them as the spatial key. Okay. So previously in DTR, the CQ is content query, PQ is spatial query. This is the content key. This is the spatial key. Okay. Previously, we add them in attention mechanism, right? We add them, and we dot product two things. Okay. And this was the situation happened in DTR, right? But now in conditional DTR, we separate their operations by concatenating them. Okay, so by concatenating key, content key and spatial key and content query and spatial query, by concatenating them and applying that product, we can obtain this type of operations, more simplified version of the attention. Okay, this has happened in conditional DTR. Okay, and they are saying that this division of spatial and content that is helpful for improving the training. Okay, and the spatial part are obtained like this. Okay, so decoder embeddings are obtained by from the object queries by using some self-attention mechanism. Okay, and we have a separate module for obtaining these partial embeddings. Okay, so first we infer the 2D coordinate. This is actually called as similar to reference point obtained in the deformable DTR. Okay, this is actually denoting the positions, actually the XY positions in the image space. And we encode, apply sigmoid to normalize it. And also we apply some positional encodings using some sinusoidal function. And actually that is same manner when we decode, when we make the positional encodings for this Euclid, the encoder output. Okay. And also, okay, so this sinusoidal encoding is happened to align this reference point, the positional space. We first obtain the positional space, but we further align it with the key positional space of the key, okay, by applying the same function, same sinusoidal function on that. Okay. And also, we also scale it. So this is the sum transform function to further transform this sinusoidal function, okay? But actually, this T is the diagonal matrix having entries only in the diagonals and having all zero. So actually, this is actually multiplying some scalar lambda to each entry of this P of S vector, right? So we directly scale the PS elements using this estimated T. So this T is further inferred to adjust the scale of the the how to say the spatial the query spatial query. Okay. Anyway, this PQ becomes the spatial query, and it is concatenated with the cross attention output. Okay. So this is the conditional DTR. Rather than adding these spatial and content queries, we concatenate them. Okay. And also we apply this kind of thing to be aligned with the positional encoding of the encoder. And also we have further modules to adjust their scales, okay? So in conditional DTR, you can see compared to the vanilla DTR, the performance is better, right? Okay, when you compare with the same Apple trained model, you can see the performance is far better. And using different backbone architectures, you can also see this performance was improved. And the fully converged conditional DTR, you can see it is far better than the fully converged DTR as well, okay? So this is the conditional DTR. So the high-level idea is object queries are not having spatial information, and they are not aligned with the spatial encodings of the keys, which is encoded during the encoder, right? So the authors of this paper is assuming that that is making DTR to converge slowly, right? So by explicitly giving some positional encoding for object queries, they can somehow align the position space of the queries similar to the key, and then they see the performance is far better than DTR. Okay, and it takes fewer time to converge. Okay, indeed, the assumption was correct, right? Okay, and next is the depth DTR. This paper was published in ICLR 2022. Okay, so they are still concerning about the object queries. Okay, this is not having proper spatial information yet. They are insisting that. So they are comparing the attention, visualization attention for DTR, conditional DTR, and depth DTR. Okay. So this is the attention of DTR, and they are saying that it is unconcentrated and it has too small or too big attentions. And the conditional DTR, it is better than DTR. However, its attention is more like the Gaussian distribution. And it has a circle, right? The width and height are same. And anyways, it has less information about the actual object, okay? But depth DTR, its attention is kind of sharp and also having different width and height, okay? It further consider the scale of the object, okay? So what they do in depth DTR is they actually supply the actual bounding box information, their center point, that center coordinate, and the width and height of the box as the input to the positioner, the spatial queries, okay? So previously in conditional DTR, we have this mechanism to make the spatial query, right? But here, it further have this type of spatial encoding, okay? So for Q's anchor, for each query, it apply the positional encoding to this anchor. This is actually that things. So applying positional encoding for individual elements is same as applying positional encoding for individual element and concatenating them, okay? This function, positional encoding, this is the some function that generates sinusoidal embedding from floating numbers, okay? This is coincides with the positional encoding used here, right? Okay. So previously, in DTR and conditional DTR, the queries are rather in high dimensional, and the queries are not having direct relationship between bounding box locations, okay? But they manage it as the low values for bounding boxes this time. So they can infer the bounding box at every output, right? And they can actually update these anchor boxes. And using these anchor boxes, they can encode the positional encoding, okay? This is more simpler way to manage it, to generate the positional, the spatial query, because the queries now having the bounding box values direct, so they are directly related, okay? Previously, the query values, they do not have direct relationship between to the bounding box location, but now, because we are actually using the coordinate of the box in the middle of the spatial encoding, so they are directly related, okay? That's the merit of that DTR. So this is the same as before. And actually, self-attention, the content query, positional query, the query key values are used like this, right? For the value, positional encoding is not applied, but the query and key, the positional encoding is added to the content value, okay? For cross attention, the queries are generated like this, okay? So it is the concatenation between content query and some positional, the spatial query, and it is generated like this. So it first apply positional encoding to the query locations and multiply this, which is the scale, adjusting scale, which can adjust scales of each encoded positions. So actually this is used similarly to previous conditional DTR, okay? Here, the key is from the image feature, right? So XY here is the XY coordinate in feature space. So this is the this is the feature map, and this is XY, and FXY. This means the n-dimensional vector in this location, right? This is the content feature, and positional encoding is applied for that X and Y, right? So this is the key from the encoder output, and value is also this, becoming this in cross attention mechanism, okay? So anyway, the positional, these queries are also having some spatial information now, right? But it is similar to conditional DTR, but this part is slightly different. So previously, positional encoding was applied to X and X reference, but now this is further inferred from the content query via some linear layer, and these values are actually adjusting. It is differentiating the width and height of the attention. So previously in conditional DTR, attentions are rather in square, in circle manner, but depth DTR, it has different width and height in attention. And actually, sorry, this width and height, it is inferred from the query, and they are multiplied when making some attention, actual attention, okay? The query key values are samely constituted with the conditional DTR. However, when calculating the attentions, this additional width and height information is obtained. So actually here it is visualized. So anchor boxes are used, and not here, I think. So here is more obvious. So this is the anchor box information. And here, when making query key values, making queries, X, Y are used, okay? These are same for this conditional DTR, right? This X and Y were used. But when calculating the actual cross attention, W and H are further used, okay? So their attention becoming to have different width and height, okay? And actually these residuals are outputted, and they make updated anchor box and further used to the next layers, okay? This is depth DTR. And also, this is also written in the paper. So previously, these temperatures are used, okay? So I saw that this temperature is this value. No. This is temperature, maybe. I'm not. Anyway, for the NLP task, these temperatures are set to 10,000, but the authors are pointing out that temperature 1 is, anyways, if temperatures are becoming small, the attentions are becoming sharp, okay? So it affects the temperature, it affects the size of the positional priors, okay? The less values will improving the positional priors to be sharp, okay? So they adjust these temperature values as well, okay? They further conduct this tuning, okay? When applying this positional encoding function. So in here, previously there are temperatures are set for NLP task, but in here, the authors are insisting that they adjust it towards the spatial task, okay? It further improved the performance, okay? Anyway, that DTR here, previously in DTR, the queries does not have any spatial meaning, right? But in conditional DTR, it gradually have X and Y positional information, and the performance are getting better. In DAB DTR, that DTR, it further have width and height value, and it further improve the performance, okay? So this is the comparison to previous algorithm. They actually apply DAV to deformable DTRs, and they are saying that the performance are gradually improving, okay? And they are comparing algorithms to the DTR and conditional DTR, and DTR takes a lot of epochs. Normally, it takes 500 epochs to fully converge, but DTR and conditional DTR, it takes less time, only 50 epochs to converge, and depth DTR, it is better than conditional DTR, okay? So this is the story to give some spatial meaning to the object queries, okay? So far, previous works focused on improving the decoder by improving their queries, right? But this DNDTR is proposing another scheme to improve the training of the DTR. It also accelerates the training of the DTR. So they are pointing out that the bipartite graph matching is not successful, and it hinders the fast convergence, okay? So they are saying that in early stage of the DTR training, let's say there are 5 ground truths in an image, in a training image, but we have 300 to 500 object queries, right? And each object queries have to be matched to ground truths, okay? We have the Hungarian matching algorithm, okay? And then matched predictions are applied with the MSE rules, right? But let's say first the maybe ones are 100s, 200s, and fifths and 95ths. Let's say these object queries are close to the ground truth value. Let's say like that. Then we will apply MSE loss for this output, this object queries output to make them close to the ground truth. Okay. And rest, we will apply MSE loss, but we have to make it close to the background. Okay. This is happened during the DTR training. Okay. But when first epoch, in the first epoch, these are matched sets, but let's say in the second epoch, these sets are dynamically changed, like other sets, like these sets are obtained to match to the ground truth in second epoch, maybe. And third, it also changed, right? Then the training is not becoming too unstable. That's the thing what this paper is pointing out. Okay, so ideally, these selected object queries needs to be stable during the training. Okay, then they will be gradually similar to their ground truth values, and the training converges fast. Okay, but in the practice, these selected, these matched object queries are not stable, especially in the early stage of the training. Okay, and that makes the slow convergence. So to stabilize the graph matching, the bipartite graph matching, this DNDTR is proposed. Okay. So it is slightly different to previous algorithms. In previous algorithms, they are wanting to improve object queries having some spatial meaning. Okay. But here, they are saying, they are pointing out another problems in the training of the DTR, which is happened during the bipartite matching. Okay, the matched object queries are not stable in the early stage of the training. Okay, it can hinder the fast convergence. Okay, so authors are saying that DTR-like models their training happens in two stages. First, good anchor points are obtained, and then the fine details, the relative offsets are further optimized. Okay. So the second part is not trivial to optimize when the first part is not matured. Okay. So first, during the DTI training, they are saying that first, they train to obtain good anchor. Roughly, they match the object queries to the ground truth, and then they fine-tune the details. Okay. So by involving some denoising task in the middle of the DTI training, they are arguing that the DTI training becoming more stable. Okay. So this is the graph drawn for three types of DTRs: the original DTR, depth DTR, and DN DTR. And let's say there are M ground truths. Let's say this M is 5. And this N is 300 to 500, right? This is the object query number. This is the ground truth number. And if O and I is matched to TM, this is I's layers prediction. Not I's, this is epoch. I is index for epoch. So if N's object query is matched with M's ground truth in I's epoch, we set this V, IN as M. And if it matches with nothing, it means background, right? Then we will set it as -1. And I think this should be N. Anyway, if I's epochs, this match value V is not same as I-1's epoch value, then it means for that prediction, the bipartite matching was changed, okay? So this is indicating that for that object query, the I's and I-1's I's and I-1's matching, bipartite matching result was changed. If they are not same, it means they are becoming different. Then it becomes 1. Otherwise, it will become 0, right? And if we add them, this IS means the number of differently matched the sample number, right? So if this value is larger, it means the training is not stable. So in early epochs, this could be large, okay, but gradually it would be getting smaller. But in depth detail, still this kind of fluctuation occurs. But in DN detail, there are some fluctuation, but still far less than other details, okay? So anyways, they are pointing out this instability. This is measure for stability of the training, okay, occurred by the bipartite matching, okay? So what they actually do is this thing, okay? Actually, these denoising things happened during training stage only. And testing, we do not use this. Not happened during testing, okay? And there are actually denoising part and matching part, okay? And also it happened only in decoder, okay? Decoder is now composed of 2 parts, denoising part and matching part. Matching part is same as previous details. Actually, matching part, you can sync the original detail. And we have additional denoising part. And what they do is they apply some noise plus ground truth. So here, they input some boxes and by applying some noise to this ground truth. And their task is to denoise it to estimate the original ground truth. And actually, there could be multiple sets of noised ground truth. So we call this as denoising group. 0, 1, and there are actually multiple denoising groups. Okay. This is the DN-detail architecture. So for denoising groups, we denoise their noise. Okay, that's the task of denoised group. And we have multiple denoising group. And actually, they apply some attentions between these queries, right? This matching part and denoising part, they will be applied with the attention mechanism. But we will use some mask when applying the attentions. So there are some masking like this, happened like this. So, okay. This is meaning not activated regions. So group 1, group 0 is not attended with matching part. And also it is not attended with other denoising groups. Samely for group 1, denoising group 1, it is not attended with the other denoising group and also with matching part. But matching part, it can be attended with other denoising groups freely, okay? So this type of attention mask is used. So that is actually visualized here. So this denoising group only propagated to this, not attended to other part. And also this part, denoising groups are not attended to this matching part, okay? They are only going to their output, but matching part freely can attend it with other part, okay? Okay. Actually, there can be P denoising groups, P denoising groups, and in each denoising group, it has m number of queries, okay? Actually, m is coincides with number of ground truths, okay? So it prevents matching part refer to denoising part. It prevents the reference among denoising groups, okay? And for noising, the center is shifted, okay? The ground truth, its values are shifted by some noise, and their scales are constrained like this, okay? And also the scale, width and height, they are also added with some noise. And also they are randomly flipped, okay? Anyway, they are from this noised ground truth, they are learned to denoise it, okay? That is the DN-DTR, okay? So by attending with this ground truth, actually the matching part, the high level idea is this becomes more stable by seeing the values which is close to the ground truth, okay? So previously, what the problem, what DNDTR is motivated was due to this fact. So the unstable bipartite matching happened in the early stage of the training, right? So these matched queries, object query bounding box outputs are sometimes not very close to the ground truth. So they can be fluctuated during the early stage of the training, right? But by supplying some noised ground truth as the input, as the additional queries, somehow the transformers are seeing the ground truth value, right? They are noised, but still have some values close to the ground truth, okay? Because of that, the training becomes stabilized, okay? So relative offset learning, so by using some this denoising task, anyways, seeing some, even though they are noised, somehow good anchor is secured by the denoised, noised queries. So the DTR rather concentrate on the offset learning, right? By supplying the noised queries, okay? So another merit of the DN-DTR is they are applied to almost every DTR-like method, okay? So anyway, they could DN could be applied to DTR using the ResNet 50 as the backbone, okay? They surpass almost all method, okay? Okay, and also the backbone is changed and they applied DN. And also backbone is changed and they applied DN. And here similar, right? Also, they can apply DN for multiple algorithms. DN for deformable DTR, DN for DTR, deformable DTR, DN for DTR, and so on. Okay, so this kind of DN algorithm is could be easily applied to diverse DTR-like models. That's another merit of this DN DTR. Okay, it can improve the performance anyway. And the next thing is Dino, which is published in ICLR 23. It is the state-of-the-art DTR architecture till now. And it's kind of combination of three algorithms we saw so far: the deformable algorithm, depth DTR, and DN DTR. So it involves the denoising training, and also it involves the query initialize using the spatial information, and also it has the iterative box prediction. Okay. So in very early epochs, it achieves very good performance compared to others. Okay. And also model size is less. So the Dino, its whole pipeline looks like this. So it involves the multi-scale features and also having some positional embedding modules. And this is the encoder layer. And this is the decoder layer, similar to deformable DTR. It have the two-stage architecture like this. It first estimate object proposal and use it as the spatial encoding of the object queries. And also it have the denoising module, but this time it has the contrastive denoising module to further improve the denoising module. Okay. So, and it also iteratively improve the bounding box information. Okay. This is the Deno architecture. Firstly, I want to explain the contrastive denoising training. So the denoising training, which is proposed in DNDTR, was effective for helping the DTR converge fast. It was effective for queries having ground truth box. Okay, it only applies denoising for ground truth for sample. It generates m queries, which is the number of ground truths. Okay, so for positions which have ground truth object, this denoising is effective, but it lacks the ability to estimate background as no object, since there's no ground truth boxes for the background, and we do not involve this denoising algorithm for background. This denoising is only applied to the location where the ground truths are there, right? So because of that, previous DN mechanism was applied only where the ground truth boxes are there. And when there is background, this denoising was not appeared, okay? But this can be relieved via CDN training. So they propose contrastive learning for this denoising. So they have multiple groups, right? First is the positive, the other is negative. For the positive, they are trained to reconstruct the ground truth. This is the denoised, this is the noised query, right, from the ground truth. But here, negative queries, we will map them to no object. Okay. These paired queries are becoming one CDN group. Okay. This is becoming another CDN group. So positive queries, if we apply noise scale smaller than lambda 1, it is close to the ground truth. Okay. These positive queries are queries having similar values to the ground truth because we constrain the amount of noise to lambda 1, less than lambda 1, so they are still close to the ground truth. For negative queries, we apply noise larger than lambda 1 but smaller than lambda 2. This lambda 1, lambda 2 will be heuristically setted later. So this is the ground truth. These yellow are positive. Their noise scale is less than lambda 1. So they are called as positive samples. But if samples their noise are larger than lambda 1 but less than lambda 2, they are far from ground truth, right? But they are not that far from ground truth. So this is actually hard negative samples. Okay. If some samples are located here, then they are far different from the ground truth. So they are easy samples, right? But samples located nearby the ground truth are the most difficult negative samples, right? we have to map it to no object. Okay. By involving this stream, Dino becomes more robust. Okay. That's the thing what the CDN is insisting. And another thing is, previously in deformable DTR, these anchors, these object proposals are used to further improve the object queries. Okay, we can give some positional information to the queries. Okay, and also in here we give it. But here they say this is the content and this is the positional queries. For the content query, we do not giving this kind of spatial information is better, right? So in Dino, for content query, they do not use this object proposal information, but for positional query, for spatial query, they will use this object query information. So this is called as mixed query selection. And this is a pure query selection, which was used by the deformable DTR. And this is the static query used by DTR. Okay. By improving the query selection, the performance was also slightly improved. And previously in deformable DTR, box information was defined for each layers. Okay, we are using some residuals. We improve our bounding box at each layer, but this was done only for one. Okay, but in this Dino mechanism, they slightly fix the connections, right? So as far as I remember, I plus 1 and BI. So both I plus 1 and I's box information are applied to train the network here. Okay, so this scheme is called as look forward twice scheme. So so previously here, this layer is trained by this output only, right? The gradients are flowed from this only, right? But here, there's some direct connection to later layer. And also we have connection to current layer output. So this layer is getting the gradient from next layer. At the same time, it gets the gradient from the current layer output at the same time. So it has it is getting more information during the training. But I mean, in deformable DTR, they proposed this kind of detaching to make the training stable, right? Sometimes disconnecting some connection secures the training stability, but this paper, Dino, is insisting this connection, added connections are not spoiling the stability, but they are improving the accuracy, okay? So Dino is the state of the art now, and even the epochs required is getting smaller, Okay. So actually, this is the end of today's lecture. Okay. So we saw a couple of methods that can improve the DETRs. Okay. So maybe afterwards, if you do some project, I recommend you to use this Dino, right? Relatively rather than this pure DTR. Okay. So pure DTR, their object queries are having some problem. Okay. The first problem is object query not having any spatial meaning. Okay. And second, their bipartite matching is not stable, especially in the early training. Okay. So DN denoising mechanism was proposed to solve the second, and also to give some spatial meaning to the object query, some object query estimation or the spatial query generation were proposed. Okay, that's the thing we reviewed this lecture. Okay. Okay, thank you for listening. Thank you.